Okay. Um, let's go back to scalar products. I already defined a scalar product, but there's another version of another way to calculate the scalar product that we will need. Um, so we're going back to scalar or dot products. So you've already seen this. Let me just remind you, scalar or dot product. Two vectors. We say A and B are vectors. Okay. And then let's block the focus here. And let's say we have A here. We have B like this. There's an angle between. And we have that A dot with B is the scalar or the dot product. And the formula we had is the magnitude of A times the magnitude of B times the cosine of the angle between the two. Cosine of the angle between the two. Okay? Everybody good with that? Okay. By the way, this was the magnitude. So if I have A, that's the magnitude of the vector A. Now, suppose I had components AX and AY. Then you remember how to get the magnitude, right? You take that square root, and inside the square root you have AX squared plus AY squared. Magnitudes. So if you're told you have some components AX squared plus AY squared. Now, in your homework, they start to give you some stuff with 3 dimensions instead of just 2 dimensions. So if it was in 3 dimensions, it goes AX squared plus AY squared plus AZ squared. You sneak another one in there. Okay. Probably can guess if there's 4 dimensions, you put another one in there as well. Okay. And the same thing when you calculate the magnitude of B. That will be the square root of bx squared plus by squared. And if we are in 3 dimensions, and we are in 3 dimensions generally, bx squared plus by squared plus bz squared. Does anybody have questions about this? This is just the formula for the distance in 3-dimensional space. Okay. So getting the hypotenuse when you have things in 3 different perpendicular directions. Okay, now the thing I want to give you that we haven't discussed yet is we can also write the vector product A dot B can be also written as, so these are the components, AX, AY, AZ. So it's going to be AX times BX plus AY times BY plus AZ times BZ. It's not a vector. It's just the sum of the product of the X components, product of the Y components, the product of the Z components. You add them together. So the way right, so let me just write it out this way. So we have these 3 components. We have these 3 components. What you do is you multiply these together. So you get AX, BX. You multiply these together. You have AY, BY. And then you multiply these together, and you get AZ, BZ. And then you add them together, and that's the dot product. Okay? So everybody's good with that? How many of you have seen this one before? It gives the same answer. It gives exactly the same answer. I should mention there's a special case. Suppose I were to do the dot product of a vector with itself. Let's just see what happens if I do A dotted with A. Okay. If I do A dotted with A, vector with itself, I would get AX times AX, or AX squared, AY times AY, plus AZ times AZ. And you'll notice that looks a lot like this thing over here, right? Ax squared, ay squared, az squared, all added together. Okay. So that means that when I do a dot product of the vector with itself, it will be the square of the magnitude, or the way we would write it is a magnitude squared. Okay. Any questions about this? Okay. All right. Now, the fact that you have two different ways of calculating the dot product means that you can actually go between the two formulas. You can calculate it one way, you can calculate it the other way, and this is actually very often a very fast way to get the angle between two vectors. So we'll do a quicker example towards the end of class, but if I gave you the components of some vector over here, components of another vector over here, and I'd ask you what is the angle between them. Okay? If you're like me, it's kind of hard to picture like 1, 2, minus 3, and 3, 1, 4 over here and get the angle between them. I can't do that. But if you calculate the dot product between the two vectors, a dot b, like this, and that's a pretty straightforward calculation if you know the components, then you can calculate the dot product this way as a product of the magnitudes times the cosine of the angle. Then you can solve for the cosine of the angle. You see that? Okay, we'll do a quicker example on that. Okay, now the other thing I wanted to mention, sort of going back again to a more detailed view of something that we've already done, a little bit more advanced. Let's talk about the work done by a non-constant or a varying force. Okay, so work done by a varying force. What's an example of a varying force or non-constant force? Well, I now have a spring. I pulled one up here. Okay, so if I displace the spring just a little bit, so it's in its equilibrium right now, and now if I pull a little bit of displacement, there's a little bit of a force. If I pull a little bit harder, it's more of a force. If I pull even harder, it gets even stronger, and it's pulling me in. Okay. Now, if I compress the spring, I have to stabilize it a bit so it doesn't pop out of my hands. If I compress the spring a little bit, it pushes out. If I compress it further, it pushes out even stronger and even stronger. Okay. So this is an example of a varying force. As I pull, it changes with distance. Okay. And so that's a more complicated case. And we have to consider the work done. So for a force that is not constant, what we do is we just break up the displacements into small pieces. Break up the displacements into small pieces. Not small pieces. Okay, so let's make life simple. Let's say the displacement's only in the x direction. It's only in the x direction. Okay. Suppose the displacement is in the x. Okay, then we can just focus on the x component of the force. So let's suppose somebody gave you a plot of the force, its component in the x direction, and we're going to plot it versus x. So a very good example would be the spring force, right? So we know the spring force. Remember we did that last time, Fx is equal to minus k times x. But it could be some other force. Like just make a general curve like this. Okay, some function like that. And what we're going to do to figure out how much work it does going from, let's say, I didn't need to go that far. Now my initials, my finals were over there, but okay, I'll live with that. Let's say that's the initial. It goes up to some final value over there. What we do is we're going to break it up into little pieces. Little pieces like this. And then add up the work done for each little piece, because on each little piece, the force doesn't change that much. Okay, and then this is how calculus works. You break everything up, and you take the limit as the pieces get infinitesimally small. Okay, so the work will be remember we call that capital W. Will be the sum of all these little pieces. Let's call them delta W over all the small displacements. We add them up like this. And so in other words, here's a little delta W that we get from this little piece here with some little delta X. And then this value of Fx here is what we need to calculate the work for that piece. Okay, so for each of these small little displacements, we have the work done will be Fx at this value of x times delta x. Okay. It's just the formula F times D, because Fx is in, for you it's this way, Fx is in the x direction, delta x is also in the direction. There's no cosine, or the cosine of 0 is 1. Okay. Any questions about this? So if you take the limit as these little pieces go to 0 in width, then we get that W is equal to the integral from x initial to x final, or xi, xf if you want, and it will be fx dx, the integral fx. Yeah.
In this class, are we going to have to deal with where like the force and the distance are both functions of time?
We won't make life that complicated for you. Okay. Other questions? So what you end up getting then, if you want it as a, just think conceptually, if we have a plot of fx versus x, and we have some curve, then the area under the curve, so this is the actual plot of the function force, fx versus x, then the area under curve is the work done by F, the force. Let's say the x component of so we're just considering the simple case where it's only going in one direction. Okay. Are there any questions about this? Okay. We've seen stuff like this before, so hopefully that's pretty familiar. Okay, now let's get back to this thing, what we were talking about with conservation of energy. Okay. So there are maybe two really big things we do in this class that's supposed to stay with you throughout your whole life. One was Newton's second law, F equals m, F net is equal to ma. You're going to hopefully use that somewhere in your career beyond this class. Definitely if you take 184, you'll use it all the time. But beyond physics class. The other one is the conservation of energy. And so that's what we're going to talk about now. Okay. So let's first define what we mean by the mechanical energy. The mechanical energy, and so we can write it as E, so MEC for mechanical, or if more often, because I'm too lazy to write all these little subscripts and they get in the way and they're annoying and everything, so we'll just write it as plain old E and have in mind that's the mechanical energy. Okay. That's usually what I'll just write, E. Okay, so the mechanical energy, E mechanical, or just plain old E, is the sum of the kinetic energy, we call it capital K, and all the potential energies. There could be several kinds. Potential energies U of our system. Okay, remember the potential energy is you have to have a conservative force, one that, oh, I'm sorry, I rebooted this thing and then I never really started it. It'll be the screen over here. Remember we said if you have a conservative force, then the work that it does is independent of the path it takes from the initial to the end. Okay, if I go from here to here like this, or here like that, gravity does the same amount of work. And then if I have a conservative force, then I can define a potential energy. And we did that for gravity. It was just, remember, m times g times y, where m is the mass, g is 9.8 meters per second squared, and y was the height relative to some reference height, like the table. And then we said for the spring, we could also do the same thing. We called x the amount of displacement from the relaxed position of the spring. It could be positive when you stretch it, or it could be negative when you compress it. And in that case, the potential energy for the spring was 1/2 times k, what k is the spring constant, times x squared. Okay. So these are the types of potential energies I'm talking about here. And the definition then of the mechanical energy, I'll just write it as E. And this is the mechanical energy. This will be equal to the potential energy, the kinetic energy plus U, the potential energy. Okay. Now, the reason we call it mechanical energy is so that we're quantifying only certain types of energies, and there are things we are not considering. So we don't consider the following types of energy. Chemical energy. You know, the amount of energy stored in a battery or a chemical battery, or maybe the amount of energy stored when you eat something. Maybe there's energy in that food. We don't, since I mentioned the bodies, we don't consider the energy stored in your body. And we don't consider heat. Oops. We could go on. We could talk about the energy stored in sound. Why are we ignoring these things? Because they're really complicated. Okay. This mechanical energy stuff with kinetic and potential, they are pretty easy, or not easy, but they follow very simple rules at least. Okay. Any questions about this? Yeah.
Are there non-mechanical conservative forces?
Non-mechanical conservative forces. So
to the point where you have potential energies that aren't mechanical?
So the definition is that if you can define a potential energy, then it will be included in mechanical. So just by definition. So you can have very unusual potential energies that you might not really think of. For example, if I had a string that could be twisted, you can define a potential energy associated with the angle you twist it. And then you can have what's called a torsion pendulum problem. Okay, other questions? Let's go on. Now, okay, so I've been talking about, all right, so now I can finally, let's make this, oh, there it goes, okay. So we've been talking about energy conservation, so let's write it down. The energy conservation principle. And the statement is as follows. In an isolated system with only conservative forces, the total initial mechanical energy equals the total final mechanical energy. All right. Okay, so if I write this as EI for initial is equal to EF for final. So this is initial, and this is final. And then I can break apart each of these mechanical energies into kinetic initial plus potential initial. Okay? Whatever potential energy we're talking about, either spring or gravity. And that must be equal to K final plus U final. So this is basically how I set up problems when I'm doing conservation of energy. Any questions about this? And this is actually why we call it conservative force, because with these conservative forces where the work done is independent of the path it takes from initial to final, the total mechanical energy is conserved. It doesn't change with time. Let's do an example. Okay, it's going to be kind of like this rolling ball here. Let's start on a new page. So remember, this Ki plus Ui is equal to Kf plus Uf. Let's do an example together. Okay, let's say we have some, that's supposed to be just a very complicated track. And we have some initial, we have a cart on this track. I have a ball, this time it's a cart. So let's say a cart is sliding on a frictionless track. By track, I mean this kind of a thing you see right here. And when it is at height 2.0 meters from the floor, the speed is 12 meters per second. When it is at height 2.5 meters from the floor, what is its speed? Okay. Now you can kind of see how little information I've given you. I told you nothing about the track. Right? I didn't say it was a straight track, it was a curved track, nothing. I draw this useless figure here, which you realize isn't supposed to help you in any way, okay? And all I tell you is when it's at height 2 meters above the floor, it's moving with 12 meters per second. When it's at 2.5, I want to know the answer. Notice I didn't even tell you the mass of the part of the cart, right? So this is why energy conservation, if you can solve a problem with energy conservation, it's really efficient. It's really easy to get the answer compared to anything else. Because you could imagine suppose I did tell you everything about the column. I told you it was like an X. The track had an X to the fourth shape to it, something really complicated. Okay? And then you started it over here with 12 meters per second. And then you're trying to calculate what its speed is, whatever it is. Just imagine how hard that problem would be. Right? It would be horrible. But we can solve it without even knowing anything about the details of this. And I'll show you how quickly we can do it. All right, so first let's look initially. The way I like to do is just write down all of these things. Initially, the kinetic energy, let's figure it out. Now, we don't know the mass, but the mass is going to drop out of the problem. There will be m's in front of everything. So let's just call the mass capital M. And so we'll say 1/2 capital M, the initial squared. Okay? And then we will have 1/2 times M, which we don't know, times the speed. Initial is, I'm taking this as the initial. Okay, and that will be 2. Sorry, that will be 12. This is 12. Okay, I'm going to leave off the units, otherwise there'll be m's coming from meters. That will be confusing because I have a capital M here, so we'll just leave off all the units. And so I'll have 144 is 12 squared divided by 272. So I'll have 72m. Okay, everybody's with me so far? Okay, now let's calculate the gravitational potential energy in the initial case. Our height is, okay, so remember what is the formula? It's m times g times y, and since I want the initial height, I will call it m, I'll call it yi. So this is equal to, that should have been capital M to be consistent. Sorry about that. So then I will have m times 9.80 times the height, which is 2.0. And so I end up with 19.6 times capital M. Okay. Everybody's agreeing with me on that? Now let's get what happens for the final case. Okay, so we have the final case where it's 2.5 meters from the floor. So we have K final. So I'll have 1/2 M V final squared. Okay, this seems to be the thing I'm trying to solve for, so I'm just going to have to leave it as it is. So let's just leave that. We don't have anything we can do with that. Okay. Now we have the potential energy, U final. So U final is M times G times Y, but since it's final, I'll call it Y sub F. Okay. Is everybody following? I'm just using the formulas for kinetic energy and potential energy. So we have m times 9.80 times the final height, which is 2.5. And so we get, that's about 24.5 times m. All right. Is everybody with me still? Okay. Now we'll use that magic formula that total mechanical energy is conserved. Conservation of energy. So the way I like to write it down is just simply, I write Ki plus Ui is equal to Kf plus Uf. Right? And then I just plug in all of the things we know. Okay? So the initial, I actually wanted to write in the F's over here and the I's over here, but it doesn't matter. Okay, so we have 72 times m. And then we have plus 19.6 times m. Then we have the thing we don't know, 1/2 V final squared, plus 24.5 m. Okay. Did everybody follow that? Just plugged in all the things. Okay, that's your conservation of energy. That was the big new step, energy conservation. Okay, now we can simplify everything here. We get 1/2 mv final squared is equal to, if I take 72 plus 19.6 minus 24.5, that comes up to 76.1 m. The m's cancel out, which is good because I didn't know what m was. Okay, then multiply by 2, and then we'll get and then take the square root. So 2 times 67.1, take the square root, and that comes out to 11.6, and I'll put the units in meters per second. Okay, everybody's follow that? It was not that hard, right? You just say Ki plus Ui is equal to Kf plus Uf, and that's all there is. Questions? Any questions about this? So you just learned the second big topic of the course. Everything else from here on is a little bit less important, but it's still useful stuff. Okay, now, in the time remaining, let's do a couple of quicker questions. Okay, so there'll be two quicker questions. They'll be related to each other. So the question is, what is A dot B? Okay, the values choices are right. And where is my quicker thing gone? Oops. Okay. Give you another 30 seconds. If you're trying to find cosine of theta, do all that. That's not how you're supposed to do it. Okay, everybody had a chance to respond? If not, go ahead, do it now. And let's see what people have said. All right, a lot of people say C. All right, so we know the formula. Formula is A dot B. We're going to do the complement formulas. AX times BX plus AY times BY plus AZ times BZ. So we have 1 times minus 2, these two guys. Then we have 1 times 0, doesn't do anything, plus 1 times 4. So we have minus 2, 0, 4, that comes out to 2. Okay. So now we know the dot product is 2. The next quicker question will be a little bit more challenging, but not overly so. A is equal to 1. It's the same vectors. I'm not changing anything. Okay, question is determine the angle between A and B. Okay, when people talk about the angle between two vectors, they generally want an angle that's between 0 and 180. They don't just the depth. You know, you could call 90 degrees 270 degrees going the other way, but the definition is between 0 and 180, by the way. Okay. So we have A 25, D 37, C 58 degrees, D 75 degrees, E 90 degrees. Okay, so let's give that a shot. The dot product, if you forgot already, if you forgot, calculate it again. So after you do this problem, you'll be in good shape for all the problems in your homework assignment. Okay, I'll give you another 30 seconds, and then we'll go over it. And I'll be it. All right, if you haven't replied yet, go ahead and make your choice. Okay. All right, so let's close it up and see what people have said. All right, a lot of D's. Let's see. So we already know the dot product. We did it before. A dot B, when we did it in terms of confidence, we found it was equal to 2. Okay? So we don't have to do that again. It was just, we just did that. So now we can also say A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay? But what is the magnitude of A? That's, if you want, this is the more descriptive symbol for the magnitude of the vector. That is the square root of the sum of the squares. 1 squared, oh, you can't see that, 1 squared plus 1 squared plus 1 squared. So that comes out to the square root of 3. Let's just read it, let's just leave it as square root of 3. Or 1.73 if you want. And the magnitude of B is the square root of the sum of the squares minus 2 squared plus 0 squared plus 4 squared. So 2 minus 2 squared plus 4 squared is 20. That comes out to the square root of 20. Okay, so now we have AB, so that's square root of 3 times square root of 20 is equal to 2. Okay, so we have square root of 3 times square root of 20 cosine theta, that's what this is. And that must be equal to 2. Because those are both the dot product. Okay. So now we have cosine of theta is equal to 2 over the square root of 3 and the square root of 20 multiplied together. And we can solve using the inverse cosine, and that comes out to 75 degrees. Okay. Any questions about that? All right. Then have a good weekend, do your homework, and I'll see you on Monday.
I did the 4.1 like when it's
Yeah.
there's like 5 questions.
Great. I started off okay, but like now I'm not doing too good. I want to try to like.
Okay. Yeah, I've office hours every day. After every class. Yeah.
I just wanted to double check. I won't be able to make it today,
Yeah.
but I have to be ready for the next.
Yeah. Okay.
Yeah, definitely Monday.
All right.
Thank you so much.
Sure.